Hello everyone and welcome to this new video. In this video we will talk about reverse engineering and about crackmes. So I hope it is a fun video. I hope you learn something out of it. If you do, subscribe to the project and you can also support me on Patreon. Thank you very much and enjoy the video. So when we talk about reverse engineering is about taking a binary and understanding the logic in which it was written, like the code, the high level code. Typically, we start from the high level code, like for example, C, C++ or something, whatever, like a high level language. And then this is compiled down into assembly. So the programmer sees the code and then the binary contains the code itself. Reverse engineering is about going backwards. So this is reverse engineering. How would you learn reverse engineering? You just have to practice the act of reading assembly, reading low-level code and trying to understand the high-level logic. Try to understand what it is actually doing. And for this end, crackmes are an extremely good educational resource. Now, what is a crackme? In the context of software security and capture the flags, a crackme is a program developed intentionally in order to be reverse engineered, like in order to apply our reverse engineering skills, to be cracked as a challenge in order to practice our skills in reverse engineering. Now, if you want to find crackmes, there are a bunch of websites. Here I just put 3 of them, and today we will use crackmes.one. There's also crackme.app, there's also the forum.tats4u. There are a bunch of different resources, just gonna focus on these ones for now. So, in this video I will show 2 particular crackmes, and here you can find the hash of these crackmes. Specifically, here if you go to the crackmes.one, here you can find the relative page. And the first one is going to be an easy one. The second one is going to be a medium one, sort of like easy to medium, just to get started. So let's see the easy ones. The easy one. We can, so the author is user with this number of R's. You can read it. Here is the hash. Here is the URL. And basically we can just wget it. We can just download it. So let's just do that. So crackmes, and we find, so this is the other one. So let's remove it for now. So let's download it with wget, and we can unzip it. And when you download the crackmes from this website, from crackmes.one, the password is either crackmes.one or crackmes.de, this one. So the first thing we can do to understand what's going on with this binary is you can just check out the file. Let's see here. Okay, file crackme. So we have a 64-bit ELF executable. This is a Pi executable and it is dynamically linked. It means that it uses, of course, the typical libraries like the libc library. Now, you don't really want to execute this kind of programs that you download unless you know that they are safe. If you don't know that they are safe, you can use a virtual machine. So basically, that's the idea. For these crackmes, I've checked that they are safe so I can execute them on my machine, but in general, be careful when you do that. So that's one thing. Another thing that we can do in terms of like understanding the capabilities of our binary is run a simple checksec to understand how it is configured. So as you can see here, we have the canary, we have the protection of the stack memory, it's not executable, we have the PA enabled. And so basically this is like a classical configuration of a, normal binary, nothing too much. We can check the dynamic libraries, and here we just link against the libc. So it's like classical situation, so not much to say there. At this point is where the fun happens, I would say, because at this point, what we can do is, okay, let's use GDB to understand the logic of this program. And the first things we can do is we can do an info functions to understand the functions defined. And if you notice these functions, what do we have here? We have the puts, we have the printf, the string compare, the fgets. So these are typical functions to deal with strings and with user input. And then we have the main, which is going to be the entry point of our program. So this is for the function. Another thing that is useful to investigate is the variables. So we can do info variables here. And as you can see here, we have a bunch of like internal variables. stdin, completed, and then we have this stored password, which to be honest already looks suspicious. But after having analyzed functions and variables, let's see the code itself. So we do a this main, and here we have the assembly. So let's try to put it all in one screen if we can. This main, and pretty much this is the entire assembly. Now, reverse engineering is about taking this assembly and understanding it step by step to see what it does basically. So let's try to read it basically. That's our objective. So first function is this endbr64. This has to do with a mechanism called set, which stands for control flow enforcement. Control flow enforcement technology. Now, we don't really want to look at this mechanism in depth in this video, but just so you know, this has to do with set. Then we have the typical function prolog in which we set up, we save the RBP and we set up the new RSP. So I've talked already about this in one of my previous video over binary exploitation. This is like a typical thing that is always done. Then we allocate memory over the stack frame for the current function, and we allocate this number of bytes, so 0x70. Then these other instructions have to do with the setting up of the canary mechanism, this one. This is the canary that is used also as a technology to help with binary exploitation. At this point we have XOR. When we see XOR EAX like this, we are pretty much cleaning out this particular register, so we're just cleaning it out. At this point we have a call to printf, and before the call to printf, we have to, when we call a function in the C code, we just do printf, and then we put the arguments, right? Now in assembly, we're gonna have a call instruction, and before the call instruction, we're gonna prepare the arguments over the registers. Because remember, this is a 64-bit, which means that arguments are first passed through the registers and then through the stack. So, what kind of arguments do we prepare? Well, first of all, here we load an address into racks, and then we move this address from racks to RDI. So basically, before the call to printf in RDI, we will have the address over this particular value, which is this one, is this address. Now, what is gonna be is gonna be the actual format string. And if we analyze it with GDB, if we just say let's do quit, and then I say xs0x200b, here we get the first string, enter password. This is the first interaction with the user, the first thing that is printed to the screen. And so this is the setup of printf. Here we put into EAX0, so we just clear out EAX, and basically then we call printf. So that's it, we don't have any other arguments other than the format string itself. Then we have another call. This time though, the call is an fgets call. So, and by the way, when we are developing this intuition over the program, we can also put it into code in a way. Let's do cmod here. So basically what we have is we have main, and in the main function we do the following things. We're gonna say printf of enter password, and then we see what happens next. Then we do an fgets. Now fgets, what are the arguments of this fgets? Well, basically, let's just zoom it a little bit here. Perfect. So here we are moving this value into RDX. Then, and this value, by the way, is the standard input. So this is the value that identifies the standard input. And we move it into RDX. Then we load the address RBP minus 0x70 into racks. And then we move this particular value into ESI, so 0x64. And then we move racks into RDI. So basically into RDI, we're gonna have a particular address, and this is gonna be a particular length. Basically, what this means is that this fgets will read from the standard input, stdin, and it will write into a local buffer, because this thing was actually a buffer defined within the function. And the amount of bytes that we're gonna read is gonna be this 0x64, which in decimal, if I just do print decimal 0x64, is gonna be 100 bytes. So basically that's the idea. We're gonna read 100 bytes from the fgets. So the fgets is gonna be like, let's see, we have a local buffer. We're gonna read 100 bytes and we're gonna read it from the standard input. Now, actually, I don't remember what is the interface of fgets. Let's see. So we have fgets. We have the size, we have the stream, and we have the buffer. So yeah, exactly like this, where this buffer was defined within the function. And with respect to the size of this buffer, it might be, let's say, for example, it is 100 for now. Let's say it is 100 and let's see what happens then. So we have this situation so far. Then at this point, we're gonna test the rax value. Now, what is rax in this case? It's gonna be the return value of fgets. And if this return value is jump not equal, so here there is a jump. So the test function is gonna test, is gonna trigger some flag in the processor, basically. And then with the next instruction, with the subsequent instruction, like in this case, we have, where is it, the test? Here is the test plus 71. And then we do jump not equal. So if we are not equal, we're going to jump to main plus 98. So this one. Otherwise, if we are equal to 0, which means that if fgets is equal to 0, if this is equal to 0, what we're going to do within the if is the following thing. So in the following thing basically is we're going to load this address into rax and then move rax into RDI, and we're going to call puts. So here basically we have a puts with this particular string that is taken from this address. So we're gonna instruct the memory 0x201c, and it's gonna say error reading input. So it's gonna say error reading input, and then after that, after this puts, we're gonna move into ex0x1, and then we're gonna jump into main 188. Main 188 is gonna pretty much finish the function. So we have this if else basically, and after this thing we can just return 0. So basically that's the idea. And here, let's see, 188 like this is gonna be ret. So maybe here we return return 1. Otherwise, in this else branch, we're gonna return 0 if everything goes well, I believe. Something like this, maybe. I mean, reverse engineering is all about trying to come up with this high-level C program of the assembly. In this case, because the assembly comes from a C program. If it came from a C++ program, we would have to create the C++ program or the Rust program. Sometimes you can even use a pseudocode. The most important thing is that we're able to reconstruct the logic of the program to actually check what the program is doing. And so far it kind of makes sense, right? We just read some input user. If there is an error, we're gonna print out an error message and we're gonna return signaling that we have an error. Otherwise, we're gonna do some other stuff. Just to make sure, though, I'm just gonna check the main page for fgets, and let's see what it returns. Pointer reading stops after an EOF or a new line. If a new line is read, it is stored into the buffer. A terminating null byte is stored after the last character in the buffer. Return value, fgets return S on success and null on error. Okay, so it returns null on error, and this means pretty much 0. So null is 0 in C. So this was correct. Now at this point, remember, where were we? So at this point we checked basically, so we do this call, then we check the rax, the return value. If the return value is bad, we continue and we do this in case of error. Otherwise, we jump to the next thing here. So at this point here we are on this else branch basically. That's good. So we are here. So here we have a call to the function str cspn. So this one. So we have the function str cspn, And the arguments, so let's see first of all the main page for this str CSPN. So let's put the main page here on the right, and let's put the code on the left. So we have basically the first str CSPN. Okay, so yeah, we have the second version, const char and const char reject. So here we are expecting 2 arguments. And indeed, here we find the RDI and the RSI, which are the first 2 arguments that are set up by the function itself. So let's see if we can actually like zoom it a little bit better. So let's do this as main. And okay, so here we are basically at this point. So what do we have here? Well, in the first argument, which is RDI, we put rax. Rax is taken from RBP minus 0x70, which is our local buffer, remember. This means that this const char s is gonna be the buffer, and so this is our first argument. Then we have this other string, which is taken from the rip plus this value. It is mapped into this thing during execution. So let's check the memory. Let's check the memory. It's 0x2031. Notice that it is this particular string. So it's the /r/n. Basically, we get a value from this thing, which is an integer. Now, what does this function do, by the way? Because we still have not described what does this function do. If we check the manual for this function, this one, it says basically the str CSPN calculates the length of the initial segment of a string, which consists entirely of bytes not in reject. So the idea basically is that let's say that we have the string hello and then /r/n. Now in this case, the str CSPN would give us what kind of value? Well, it would give us the length of the initial segment until this character. So this will give us basically 1, 2, 3, 4, 5. This will give us 5. It could also give us 5 if we just have the /n, not the /r, or if we just have the /r and not the /n. Like anytime you get a byte in this set, your length counter stops and you get the length back. And so it's just a way to compute how many bytes we have until the first /r, carriage return, or /n, new line. So basically that's the idea. Now, after this, so let's do this as main. Now we are almost done pretty much. Now, after the call to this function, notice what happens in the next line. So basically in the next line, what do we have here? Well, let's do this as main again. In the next line, we have this move 0 into a particular area location. Now this area location is computed as follows. So let me zoom in a bit. Basically, let's see what we have actually. Let me just do it like this. So it's this one, right? It's this move. Now this move is gonna be 0 into RBP plus rax times 1 minus 0x70. Now this can be a bit confusing at the start, but let's break it down as follows. This memory location is at RBP minus 0x70, and remember this is the initial address of our buffer plus the value of rax. Now remember, what is the value of rax at this point in execution? It is the output value of the previous call instruction. It is the return value of the str CSPN call, which means basically that this is gonna be the buffer of some output, and we're gonna set this thing to 0, where this output was the str CSPN call. So in terms of C code, like if we have to just construct the C code, because ultimately that's what we're doing when we are reverse engineering, this instruction, the instruction at 120, is gonna be buffer of this thing equal to empty string. So that's what we have here basically. And then, so continuing at this point, we have a string compare. So we have a string compare of what? Here we have once again 2 arguments, RDI and RSI. RDI is taken from rax and rax is taken from the buffer. So the first argument is going to be the buffer RSI is taken from RDX, and RDX is taken from this address, which points to the stored password variable. Stored password, which is probably a global variable. So char stored password. Maybe this is like something like this. Let's check the content, to be honest. So let's check the content of 0x2004. It's air data. It's like this. So air data like this. And this is basically the call to the string compare. After the call to the string compare, we are gonna test once again the return value. So we have an if here with respect to this particular output. And with respect to the flows, so we have, let's see, we call this. We check for 0. I mean, here we just compute the test. If it's not equal to 0, if the EIX is not equal to 0, we jump to 168, to jump 68. Otherwise, if it is equal to 0, we execute these instructions. So if this thing is equal to 0, we execute this internal routine, which simply does a puts, and this puts is gonna print this particular string. So the one found at this address, let's check, let's see, the address is 0x2034, access granted. So this would be a, like, something went right after all. And after this puts, so we're gonna do this, let's say, and then we jump at the end, 183, we move into return 0. So basically, in this case, it would be return 0 like this. Okay, otherwise, if else, in the else branch of the string compare, what do we have? We have the test jump not equal to 168. So we do 168, we go here and we do another puts. And this other puts is gonna be of this other string. So this is gonna be 0x2043, access denied. So very simple. And then we always return 0 no matter what. So we have a return 0 in both of these branches. And basically, this is our first reverse engineered program. So what we did is we went from this view of the program, this assembly, and we have reconstructed the high level logic, which is this one, which is a pretty simple logic after all. So we get a buffer, we print some string, we read it from user input. If we have an error, we return 1 and we quit. Otherwise, if we don't have an error, we terminate the string with a new line. So we put the null character with respect to the new line. So for the first occurrence of either a /r or /n, and then we compare the input user with respect to the stored value. These are coded credentials stored in the program. If they are equal, because string compare is 0 if the strings are equal, we give access granted. Otherwise, we give access denied. So an extremely simple program that showcases the way in which we can start to read this kind of assembly. Because after all, like, let's do one last more quick round of reading. So here we have a bunch of instructions to just set up the context. And then we have a bunch of different calls. Now, if you check about it, these calls are pretty regular. They set up the arguments and they call the instruction. Set up the arguments and call the instruction. And then sometimes we have these branches, right? These ways of saying, okay, look, sometimes I have to make a call. Like, for example, let's say, in this test, actually, let's this is a bit bigger. Okay, in this test, we have, if we are not equal, we're gonna jump in here, and then we're gonna do something else. If you are equal, we're gonna do this thing. And so basically, that's the idea. So like, we just have to like understand, reconstruct the flow. Now, for doing this, of course, there are specialized programs. However, doing it by hand, as I showed, is extremely helpful at the beginning to build your intuition on the matter. And so hopefully that is useful. And so that was the first Crackme. Let's get on with the second Crackme, which is slightly harder. So let's first wget it. One second, we have to unzip it. Actually, here, let's put it to the crackmes folder and let's unzip it. The password is crackmes.1, as always. And here we have this program 2. Just analyze it. It's a 64-bit ELF executable, dynamically linked as always. Only links with the standard libc. And now we can actually get on and crack this. So we do info functions, for example. If we have a bunch of different functions, we have puts, system, smprintf, memset, and basically this is it. And also we have the start. I don't see a main in here, but maybe there is. It's just not present. Oh yeah, there's also the main. There's also the main. Sorry, here int main. Then we do info variables, and here I don't see many special variables. And then we do this as main, basically. And this as main, we get this thing. So we get this thing. We have these lines. So I would say let's do this. Let's put it into a single file. So this as main. I'm gonna take everything and I'm gonna put it into like disas.txt so that we can comment it. Actually, let's create an org mode file, disas.org, and let's just comment it basically. So I'm gonna create a bunch of different blocks, like example blocks, to comment it together with you. So first things first, we have the function prolog, we have the setting up of the RSP, like this one. This initial thing is sort of like function prolog setup stack. Then here, what do we have? Here we have a bunch of move here. So this kind of move, how do they work? This kind of move seems to be initializing local variables on the stack. How can I tell this? Because look at this pattern. In the destination of the move, that is the places where we're actually writing, we have a bunch of RBPs minus different offsets. Now, anytime we use RBP, we are referencing local variables. So this is like setup, initialize local variables. And in C, like let's say, so this is the disas code, disassembly, and this is the high level C code that we're gonna construct as time goes on. So to construct this, basically, what I would do is I would just do the following. I would just do int main, and then here I have some arguments, int argc, char argv, and then here I have rbp minus 0x4, 0x4 with 0, 0. So this could be like, I don't know, var1, it's gonna be 0. Then I have another variable, int var2 is gonna be 0x14, which in decimal, sorry, 0x14 is supposed to be, let's see, GDB, I'm gonna print 0x14, 20, so this is gonna be 20. And then here I have these other two variables, 8 and 10, which are taken from EDI and RSI. So EDI basically is, this is taken from the arguments of the main function. Now, what are the arguments of the main function? Well, these are argc and argv basically. So that's what I believe. And specifically, I think that, let's see how they are used. So here we are initializing some local variables. Then we are comparing this rbp minus 0x8 with 0x2. Now, this looks like we are comparing the argc. Let's see what happens. So if it's not equal, so if it's different from 0x2, we're gonna jump to main 58. So 58, what we're gonna set is we're gonna set, so basically here we have, if argc is different than 2, actually let's see, if it's equal to 2 we do something, otherwise we do something else. Because if it's not equal, we're gonna jump a piece of code. Otherwise, we're gonna do this piece of code. Okay. And this piece of code is gonna call the atoy function with what? It's gonna call the atoy function with as, let's see what happens here. Here we put this variable into rax, which is RSI. So RSI into rax, and then in RDI we have rax plus 0x8. Okay, so this is interesting. It's sort of like if 0x10 is argv, then rax plus 0x8 is going to be argv of 1. So this is going to be argv of 1. And we call the atoy function here. And after we call this atoy function, basically, we are going to put into rbp minus 0x14, this one, which had the value 20, we're gonna override it with the output of a toy, and a toy will convert a string into a decimal. So that's the point of a toy, to convert a string into a decimal. And so like with this, we have our logic. So that's it for now, because after we do the call, we are gonna write EAX into RBP minus, so this is the return value, and then actually we're gonna set to 0 RBP minus 0x18, which is something different actually. It's something different. So it's sort of like something else. And otherwise, what do we do in the else branch? Well, actually, in the else branch, we don't do anything. We just continue execution as normal. So there is no else branch in this case. So that's the idea, because like the point is that if it's equal to true, if the comparison is equal, then we skip this jump and we just continue going. If the comparison is not equal to true, we take this jump, but this jump is just gonna skip us some instruction and continue execution. So basically, in high level, this is like we just have an if, but we don't have an else. Otherwise, we would have two different executions, two different branches. Okay, so and this is our program so far. So at this point, so we were saying that at this point the program introduces a new local variable in this new location. So notice that I understand that this is a new local variable because this particular offset with respect to RBP, which is 0x18, was never used before. As the offset, we use 0x4, 8, 10, 14, but never 18. And so this is a new local variable. So we're gonna say int, it's gonna be I, and it's gonna be equal to 0. Then, I mean, pretty much at this point we will have, let's see what we have here. So we introduce a new variable. We compare this variable with the value 5. So if I is, if it's, and then we say jump greater equal. So we are jumping only if it's greater or equal to main 206. So we're really going down here, 206 basically. Otherwise we do this. Okay. So we do move, we do compare. If, so basically, if instead we're not greater or equal than 5, like at the start 0 is not greater or equal than 5, we do the thing in the middle, basically. We do the thing in the middle, and notice what happens at this time. Okay, so yeah, notice this. So basically, what this looks like is this looks like a for loop. Why do I say this? Why do I say this looks like a for loop? Because basically here we have initialization, where we put this variable I equal to 0, and we check, is I greater or equal than 5? If it is, go to the end of the loop, like skip the body of the loop. This is the body of the loop. So this is the body of the loop. At the end of the body, here, what do we have? We have this piece of code which reads the local variable into a register. So it reads I into EAX. It increments EAX of 1, sort of like doing I equals I plus 1. It moves EAX into the variable I. So pretty much these three instructions, like this string instruction here, they are doing I equal I plus 1. And then we're jumping back to the beginning, back to the check, main plus 65, which is the compare check. So this is doing pretty much a for loop for I int I equals 0, I less than 5, I plus plus. So basically that's the for loop. And within this for loop, we have this body logic. So at this point, we have identified the structure of a for loop with the initialization of the variable, with the check of the condition, terminating condition, the internal body, and the update statement to increase the counter I. And so we have the following code. Like here you can see the code. Actually, maybe this one we can put into a different buffer so we can zoom in a bit more. So cmod like this. And so this is the code that we got so far. So at this point, we have seen the for loop, and we have written here on the right. So we can say beginning, like initial for loop body, for loop body. Actually, we can say for loop init. We can say for loop body, and then at the end here we can say for loop update statement. And so now we can analyze the internal body of this for loop, because of course this internal body is itself a complex sequence of instruction. And as you can see, a key ability that comes from reverse engineering is in understanding how to split up the program as a sequence of meaningful blocks. For example, in this case here, we can see a bunch of operations. Then we can see a jump equal. So we're gonna jump if something is equal. And this something is the result of this comparison, which is the result of this AND operation, which is obtained by doing this shift operation. So let's pretty much split out this thing, and let's split it until the end, this value basically. So what do we have? So here I'm just gonna put some spaces to to understand that we are inside the for loop. So what we're doing here is that we are loading these two local variables into the register EAX and ECX, and then we're loading the value 1 into EDX. Then we are shifting what? So CL represents the lower 8 bits of ECX of this particular register. What does this register contain, by the way? It contains the local variables that we are using for the for loop, so the iterator I. So basically here we are shifting the value, like we are doing a left shift, so we are shifting left like this, and what we are shifting is the 1, so we're shifting the 1 value by how much? By the I iterator. So that's the expression that we are computing up until basically this point, And so let's do. So we say 1 shifted left by I. What do we do with this thing? Well, actually we are, so at this point the result is in EDX. Then we are moving EDX into ECX, and then we are doing a bit mask, a bit AND operator between ECX and EAX. And EAX contains this local variable, which is actually the original here, the one that we initialized with 0x14 and that we updated after the atoy call. So basically this is the var2. So var2 and this thing. So that is the value that we are computing. Now at this point we are comparing this thing with 0. We are comparing the result of this expression with 0. So we say if this thing is equal to 0, so if this thing is equal to 0, we do something. So here is compute this expression. At this point we have this compare, right? So we have compare this thing with 0. If it is equal to 0, we jump. So we skip a section of the code. And as you can see here, the jump, we're going to do jump 187. We jump 187, and it's going to say jump 192. We jump 192, and we go to the end of the body of the for loop. So basically, it means that if we are different than 0, we don't do anything. Actually, no, if we are equal to 0, we don't do anything. Here I made a mistake, because if it is equal to 0, we jump only if it is equal. So if it is equal, we just basically return, which means that if it is different than 0, you can say if it is different than 0, then we do something. And since here we are doing this thing, it just means that, okay, if we are different than 0, we have the body. So the body itself, so compare value and jump and terminate the body, the for body, if it is equal to 0. At this point, we are inside this if, right? So what do we have here? Well, here we have, let's see, we have a move with a new local variable, 08. So we have a move, we have a compare, we have a jump greater equal. So like this needs to be another for loop, because if you look at the for loop structure, what you notice is that we have a move, we have a compare, we have a jump greater equal. So we have the same block of instructions. We have a different local variable, of course, because this is going to be a different like body, a different iterator. So we have a new for loop init I. Here I'm gonna put the variable of the loop. We're gonna put j in this other case. Then inside this loop, what do I have? I have a bunch of instruction. I have pretty much all these instruction. And then, so let's see. I feel like until here, I have this. This is gonna be the for loop body, the internal for loop body. And then at the end, this is gonna be the for loop update statement, like this one. For loop update statement. Why do I say that? Why did my eye see this pattern? Because look at this. So here we are using, look at this offset. Let this offset guide you. Here this offset represents our index variable, right? And we find the same offset here where we are loading it from memory into a register. We are adding one to the register and we are moving it back into the memory, basically from the registry to the memory, which means that we are updating. We are doing j equal j plus 1, and at the end of this we have a jump to 177. We have actually no, we have let's say we have this. No, we have a jump to 108, and 108 is this compare. Yes, so this looks like the update statement, and this looks like the internal body. So at this point we are dealing with this internal body of this for loop. And what do we have here? Well, here we are loading a memory from the local variable into this R6, and this is the iterator j, the internal. Actually, no, this is not the internal iterator. This is the iterator I. Is the one that we're using for the external loop. So basically, let's see here. I have to write an internal loop j equals 0. This internal loop ends when it reaches 8, basically, and then I have a j++. So this is the internal loop. Now, so this one is I. Then I'm loading this address, which points to this variable called chunks, to this chunks tagged here chunks. Okay. Then I have, so here I just loaded the address and I put it into racks. At this point, look at this. I take the racks value plus R6 times 8. So R6 times 8. R6 contains this I iterator. So this is a memory access basically that just, so let me write it internally even more. This essentially, let's see until here. This loads into racks the value chunks of I. That makes sense. Actually, here is, let's say that chunks is a sequence of bytes. Here we have 8 times I. Because here we multiply the base address, which is racks, with I times 8. So we do this. Then here we are loading the new local variable, which is the new index, which is j, into R6. And we're accessing at this point racks plus R6 times 1. So at this point, it's chunks of 8 times I and the j. So this is like, it's sort of like, let's think about this. Chunks seems to be a pointer to pointers. It's sort of like we have a series of strings, and each string is long 8 bytes. And then, so with I is going to give us the row, and j is going to give us the column within that row. So basically, this is going to load chunks in register EAX, basically. And assuming chunks is a sequence of 8 bytes, is made up of blocks of 8 bytes each. So we are assuming that chunks is a sequence of blocks where each block is 8 bytes. And if that assumption is correct, this should give us this particular value in the memory. Then we perform XOR. So we perform XOR. Perform XOR. So pretty much we are doing this XOR 5. Actually, it's 0x05. So we are doing XOR operator. Here I'm going to highlight so that it's more visible. Okay. And then what do we have here at the end? What we have here is, okay, we are moving the last 8 byte of the register EAX into DL, and here we are moving this the iterator into R6, then we are using we are moving into R6 the other iterator, and then we are here basically we are writing back the result of the XOR operator into that same memory area. So write it back into memory. That is, so here we are performing, here basically we are doing this. We are doing chunks of 8 times I j XOR equal 0x05. So basically we're doing this assuming though that chunks, so let's say char chunks, and here we can say that sort of like maybe chunks is an array of strings. So we have string 1, then string 2, but here the strings have to be 8 bytes. So it has to be 8 bytes precise. And why do I say that? Well, because here we are offsetting this, we are doing 8 times I. So I expect that each row has 8 bytes. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. So something like this. And basically that is the idea. If each row is kind of, if the row is different, it's not precisely 8 bytes, this could not work. So here we're writing it back into memory, and then we do the for loop update statement, and then we finish the other for loop. So far we've got this program. Okay, so continuing, how much is left? Okay, not too much, that's good. At this point we can go to the end, whatever, like we go to the end, it's fine. Then here we can see that we're doing the like function epilogue. Here we are doing return 0 at the end, return 0, perfect. Here at the end we are doing some call to puts. We have some call to puts, and this particular address, let's see the string that we get. It's wait a second, 0x2026, cannot access memory in that area. But okay, here it says that it cannot even find main, so I think there is a problem with just GDB. Oh, because I started GDB without the program, of course. And then I could not read this address, so 0x2026. Here I get the incorrect flag, so here I'm gonna have a puts to incorrect. Probably if we did not get what we wanted, basically. Okay, call puts. Okay, let's go up now. Let's go up and let's take it. Okay, so here we have a memset. Call memset. Okay, so here we have a memset. So after the double for, because notice that at the end here we have finished all the for. So like we are literally after the for. So here we have memset. What do we put in memset? So here we are putting, so we have not here, but here, RDI with RBP minus 0x50. So 50, I've never seen this offset, I've never seen this thing, therefore I suspect it is a new variable. Okay, so this is a new variable. Then we are doing XOR with SI, ASI, so it's gonna write 0, and then it's gonna write 27 into EDX. So here I expect a local buffer. I'm gonna write 0, and I'm gonna write 0x27 times 0. And 0x27, by the way, in decimal is 39. So I expect something like buffer, char buffer 39, something like that. And it's just gonna initialize that buffer to 0. Just gonna call 0 because here it should be 0 in SI, which should be the value that you write. So call memset, okay. Then what do we have here? Here we have a bunch of addresses loaded. And then we do an sn printf. So this is a big call to sn printf. Call sn printf. So like all of these is gonna be arguments to the sn printf call. So let's see what we are working with. So the first argument that we call this sn printf, so here I have sn printf, is gonna be this buffer. So actually this buffer is gonna work as a format string, basically. If I understand this correctly, it seems like that. And because this is what we use, this buffer thingy. Okay. Then we have SE 0x27. Okay. So SNPrintf, let's check the main page for SNPrintf, by the way. SNPrintf, let's see what it says. It says SNPrintf. Okay, look at this. We have the format string, the size. Actually, we don't have the format string. I'm sorry, the format string comes afterwards. So I just need a better description of this. So the functions SNPrintf write at most size bytes to str. No, okay. So like the first argument is the buffer in which we will write. Okay, so that makes sense. So it's the buffer in which we will write. At most, we will write 39 bytes. So this is correct because it is the size of that buffer. It is the size that we also use to initialize that buffer, basically. So that's good. So like, okay, buffer in which we will write, size that we will write, and then here we have these different chunks. Okay, so this one is the format string itself, rdx. So here we put so it points to this memory location. Let's check that memory location. Notice what we get here. Notice at the bottom here, we get this particular format string. So we're using this format string, which contains 1, 2, 3, 4, and 5 strings. And notice here, after that format string, we get 1, 2, 3, 4, and 5 chunks. Now look back at the double for that we wrote previously. Here we are doing the outermost 4 as an iteration of 5, so it goes from 0 to 4, and the innermost goes from 0 to 7. That is, it's sort of like we are changing the value of these chunks one after the other, where each chunk has size 8 bytes. So here we are loading the address of all these chunks in the various registers. So I suspect that basically here we're just gonna do chunk 1, chunk 2, chunk 3, chunk 4, chunk 5. So something like that. And this chunk 1, chunk 2, blah, 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 it's like chunk 1 is gonna be equal to chunks of like 0, something like that, right? So that points to that particular element in the array. Something like this, perfect. Notice also that some are written in the registers and some are written in the stack, because we have used all the elements of the registers. And this is also what I showcase in the format string vulnerabilities. It's just the functioning of the of the varags, these variadic functions like SNPrintf. Typical argument, first you use the registers and then you use the stack and you start writing at the RSP address, so it makes sense. Then we are initializing the rax register with 0, which is gonna contain the return value, basically. And then we call SNPrintf. So we're almost done with this thing, basically. So what remains here is that now we're gonna call a memset, we're gonna call a SNPrintf, and then we're gonna call a system. We're gonna call a system, and if the system returns 0, we're gonna jump to 371. Otherwise, we're gonna keep going, which means that if we keep going, we're gonna call puts with incorrect. Basically, it's gonna be like this. Call system. Here we have to check with what kind of string here in input. Call memset. Call SNPrintf. So this memset is for a different buffer altogether. So look at this, new offset, new buffer. So at this point here we have buffer 2. This is gonna be size 0x50. So it's gonna be PD 0x50. It's gonna be 80 characters in here. And I have this memset. So I have memset. I'm gonna have buffer 2. I'm gonna have 0, and I'm gonna have 0x50, which is 80. Then I'm gonna do another SNPrintf. So similar to this but different. It's gonna go to buffer 2. To buffer 2 as let's see here, SNPrintf. The first one is this one, RDI. Then we have R6, and this R6 is the format string. And then we have this 0x50, so 0x50, and then the format string is actually taken from the previous buffer, okay? And here we load into RDX this other string, which is taken from this address. So 0x200, which is this thing. Okay, so actually the format string comes from here, and what we put in the arguments is the buffer that we previously computed. So basically here, okay, at this point, let's explain this. So basically we declare this buffer, we initialize to 0, we use the chunks previously modified to create this first string. Then we use another string, and this one looks like a command. And in this command, there is a part that varies, right? And we use the previously created string to insert that. Okay, so that makes sense, basically. And, okay, so then we call system. So we call snprintf, like this, basically. And then we call system. Now, when we call system, we are using this string, so this buffer2. And then check return value of system. If it is 0, skip the following puts. Otherwise, execute it. So it means that if the value is different 0, we're gonna call puts with incorrect. It means that we got the incorrect command and we did not solve the crackme. So what does it mean? Now that we have analyzed all of this code, what does it mean? It means that now we have this idea of the program. What's gonna be the idea? Basically, the idea is gonna be to find an input that when processed using this kind of thing is gonna give us a command that will not print incorrect. If it prints incorrect, we have failed pretty much. Like a valid command, basically. So now, how does our input change these chunks? Well, the logic is this. Here, we are selecting single bits from our input, from our variable chu. What does it mean? Here we start with 0 to 4, right? So we have the 0th byte, then the first byte, then the first bit. So sorry, here I'm talking about bits. Then the second bit, the third bit, and the fourth bit, okay? So that's basically the idea. Now, when we do this, for example, when I is equal to 0, here we are just doing var2 and mask with 1. So we are just taking this bit, the first one. So if the first bit is 0, we're gonna XOR the first chunk with the value 0x05. If the first bit is 0, we're not gonna XOR the first chunk. If the second bit is 1, we're gonna XOR the second chunk with the 0x05, with the 5 value. So depending on the bit mask of our input, we're gonna create different chunks, which is gonna create different commands. So a simple way of like brute forcing this, basically, what is this? Is to just, which means that a simple way in which we can sort of like brute force this is just to find the correct combination of all these bit masks, which are these 1, 2, 3, 4, and 5, that give us the correct combination. So like here, the flag is the correct combination because each combination will process the chunks in a different way, and one of these way will give us a correct command at this point. Now, in this case, it's actually not hard to brute force because, well, we're talking about 5 bits, right? And if we take 2 to the 5th, it's gonna be 32. So we just have the value from 0 to 31. So basically, we have to give input to this program values from 0 to 31 and see which one creates the correct, which one does not print incorrect. For example, here I can just do it manually, basically. So I can do 2 and then I can do 0. And it's going to say incorrect. 2, 1 incorrect, 3 incorrect, 4 incorrect, 2, 4 incorrect, 5 is going to give us something, but it doesn't seem like the complete flag though. But it does not print incorrect, so this is a little bit better. 6 is going to say incorrect, 7, congrats something, 8, 9, you found the flag, but it also prints some kind of garbage before, 11, and 11 is the one that prints the full message. Congrats, you found the flag. I can keep going. Now, 11 in binary, like if we check int to bin 11, is going to be 1011. So 1011, which means that it has a 0 initially. So basically we have first, second, and fourth chunk that we XOR, and this is gonna give us our format string. If you do like 12, incorrect, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and then 32. Of course, now remember that we can even put a bigger number that has the same, like for example, this one is going to have the same Actually, it's, yes, it's, let's see, this is 3, 4, 5. This one is gonna have these bits correct, so like it's still gonna work. And this one is actually gonna be 11 plus, we do, this is like 0, 1, 2, 3, 4, and 5. So this is like 11 plus 32. 11 plus 32, which is equal to 43, should also work. So if you do 2, 43, it also work. And we can do multiples of this. So we can do plus times 2. So this is 11 plus 64, which is going to be equal to 75. Also 75 is going to work. 75 is also going to work. Why? Because they have the same bit mask, which starts, I mean, not completely the same, but the last 5 bits of all these numbers have the same bits. So they have the same last 5 bits, basically. And so this is the high-level program. And this was the, let's see where I find it. Where did I put it? And this is the assembly. So as you can see, it does take some time to disassemble it, but it can be done. Now, to finish off the video, in this video I just went manually in a very slow way, just to make you understand how it can be done. However, of course, there are better tools for this. There are tools that do this automatically. And one of these tools is GHIDRA, which is a decompiler whose job is like putting all together. We find the following code. Here we have this code basically. This one does not compile, but it's a pretty good description of what we managed to obtain. Okay, so as I was saying, so there is GHIDRA. Here I'm just going to show quickly how we can use it. So here I just downloaded it basically in the crackmes, and I've extracted, I've unzipped the folder. So I have this GHIDRA public. I'm going to execute it. Wait a second. Here I have to execute it in the previous folder. No such file. Let's see. GHIDRA, and then I have GHIDRA run. GHIDRA run. And basically, so here I'm just starting GHIDRA. And then here I have to say file, new project. I'm going to create a non-share project. I'm going to create the name of the project test just to showcase this. Then here I can import file into this project, and I'm going to import the file, the binary from the challenge. So in this case, you can see the two binary. So I'm just going to click on two. I'm just going to click on OK, and I'm going to disassemble it. I mean, it's going to decompile it. Here I click on two on the binary itself to analyze it. And here it's going to ask me what kind of analysis I want to make. I want to analyze this with the default analyzers. Just going to analyze this, and this is going to try to reconstruct the high-level logic of the program to decompile it. And as you can see here, look at this. This code, so this code, I'm just going to copy this and put it in a new buffer here. I'm going to do cmod. Notice how similar it is to the one that we found. So basically here we have a bunch of different variables. Then here we have the toy check. Here we have the double for, basically. Here we have the double for, and here we have the XOR with 5. The XOR with 5. Here we have the memset, the smprintf, the memset, the other smprintf, and the check for the system. The check for the system. And let's see the code that we brought, basically. So at the end we got this. So let's see, what about this if? So if j and 1, like, okay. But actually here it should be the same though, because here I'm using j as an iterator, but it's actually using local 20 as an iterator, while j is the variable that we read from the user. So we are using different variable names. And also it's doing this AND bitmask with this bitmask 0x1f, 0x1f. But this one should not change much, because local 20 is still from 0 to 5. And from 0 to 5, this thing should be pretty much useless, I think. So the code that we got should be really the one that of the process. And basically, this is it for this video. I just wanted to showcase how you can reverse engineering things from scratch without the compilers. Of course, if you want to do it fast, if you have a more complex project, you need the help of the compiler. However, it is still very educational to do it from scratch by hand with simple programs. Thank you very much. If you want to support my work, there is the Patreon, and to the next video.